Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to start our discussion of how to design counters. Now, before going to start our discussion of how to design a counter, first of all, let us try to understand what is the difference between your blocking assignments and non-blocking assignments. This we have discussed in our previous sessions. Let us try to understand when to use your blocking assignments and when to use your non-blocking assignments, and why we are using your blocking assignments in combinational design and why we are using our non-blocking assignments in our sequential design. Let us try to understand these particular things with some examples and let us explore this. Now, the rule here is, in the previous sessions also I have told you that your blocking assignments should be used in combinational design, and whereas your non-blocking assignments should be used in your sequential design. Should be used in your sequential design. So this is the rule which we have discussed previously, that your blocking assignment should be used in a combinational design, whereas your non-blocking assignment should be used in a sequential design. This particular rule we have already seen in our previous sessions. Now, why is such that? Let us try to understand. Let's say, now let us say we have a design like this, a AND gate and an OR gate like this, and a NOT gate connected to over it, and one OR gate. Okay, we have a design like this, and A, B, and C are our inputs, and Y is our output. Now, if we want to design this particular thing in our Verilog, first of all, we are going to declare this as wire W1 and this as wire W2. Okay, and this as our wire W3. Okay, now how to design this within an always block? Always at the rate star. What I am going to write down is, let me declare them as reg W1, W2, and W3. Okay, so W1 is equal to A and with B. I am using a blocking assignment, and W2, let's say this is W2. Okay, W2 is equal to W1 and or with C, and my Y is equal to not of W2. So this is the equations which I have written. Now, here, this is a combinational design. I am using blocking assignments. Since it is a combinational design, I am using blocking assignments. Now, here I can see that if my W1 is equal to A and with B. Okay. Now, the W2 is nothing but W1 or with C, and Y is equal to not of W2. Let us say if I am writing this same design using non-blocking assignments, then what will happen always? At the rate star begin W1 non-blocking of A and with B, and W2 non-blocking of W1 or with C, and Y non-blocking of not of W2. We have this particular design. Now what is the difference between these two? Let us try to understand. On the left hand side, we can see after this assignment has been completed, then only we are moving to the second assignment. And after this assignment, second assignment is going to be completed, we are going to third assignment. Okay, so after this first assignment is going to complete, then we are going to the second assignment, and after second assignment is going to be completed, we are going to third one. That is, one after another, sequentially, one by one step is going to happen. Here the output of this OR gate will not produce the OR gate is not going to produce any output until and unless we are going to get the output from this AND gate. You can see from the code also, until and unless we are going to get the output from this right hand side, we are not going to move to the next operation, next assignment. And until and unless we are going to complete this second assignment, we are not going to the third assignment. This is the behavior we are expecting. But on the right hand side, we can see that W1, W2, Y, all these three assignments are going to execute parallelly. So W1 will be assigned to value of A and B, and W2 will be assigned to W1 or with C, and Y will be assigned to not of W2. These three assignments are going to execute parallelly, but on the left hand side, one by one, sequentially, one by one assignment is going to happen. In the combinational circuit also we can see this type of assignment we need. So that's why we are using blocking assignments. But if we are using non-blocking assignments, everything is going to happen parallelly. Let's say suppose if your value of A is equal to 0, B is equal to 0 and C is equal to 1, then what is going to happen? If your A is equal to 0 and B is equal to 0, W1 is equal to 0. Then after W1 value has been updated, you are going to the second step. In the second step, what are you doing? In the second step, W1 is equal to 0 and C is equal to 1. So OR operation will be equal to 1. So W2 value will be updated to 1. Next, what is going to happen? Not of W2 is nothing but 1, not operation on this 1, then you are going to get 0. So finally the value of Y will be updated. Okay. But on the right hand side, if you can see, the value of A is equal to 0 and the value of B is equal to 0, W1 will be equal to 0. It will be updated to 0. But at the same time, the second operation is also going to happen. What is happening? W2 is non-blocking W1 or with C. Then what is happening? The initial value of your W1 is unknown. The initial value of your W1 is unknown and we are performing OR operation with C. So W2 will be unknown itself. And here also, since we don't know the value of W2 initially, it is unknown. So we will get the unknown value. This is the reason we are not using this non-blocking assignment. But afterwards, what happens? At the next cycle, after some time, we are going to get the updated value. The value of W1 will be updated and the value. So this is the reason we are choosing blocking assignments for combinational design and we are choosing non-blocking assignments for we are not choosing non-blocking assignments for combinational design. Now let us take the another scenario. We will try to understand one more scenario. Let's say we have a 2-bit CISO like this. This is 2D flip-flops we are going to have. This is DFF1 D flip-flop and this is one more D flip-flop, D flip-flop 2. Okay. And this is a synchronous D flip-flop. So I'm going to provide the same clock to this 2 D flip-flops. And here I'm going to apply D and the output of this is given to the second D flip-flop and we are going to get here the output. Now let's say this is Q0 and this is Q1. Now, so let's say initially Q0 is equal to 0 and Q1 is equal to 0. Okay, initially your Q0 will be equal to 0 and Q1 will be equal to 0. And at the first clock edge, your Q0 is equal to 1 and let's say we are providing the input as 101. Okay, so Q0 will be equal to 1 and Q1 will be 0 itself because these two D flip-flops are running parallelly, executing parallelly. And at the second edge, this Q0 value will be shifted towards the right and the next value will be updated to the first D flip-flop. So we will get 0. And at the third clock edge, we are going to get the next value 1 and this will be shifted to 0. So you can see in this particular code, the two D flip-flops are running parallelly. Okay. Now let's say how to write this code. Let's say I am going to declare two variables reg q0 and reg q1. Reg q0 comma q1. This is how I am going to declare and one input as serial underscore in. Okay. Now so within an always at the rate passage of clock, always at the rate passage of clock. This I'm going to write it down and always at the rate passage of clock. Now let's say Q0 I'm going to use a blocking assignment. Q0 is equal to S underscore in and here I'm going to write Q1 is equal to Q1 Q0 and followed by begin and end. And here also begin I'm going to use non-blocking assignment Q0 non-blocking of S underscore in and Q1 non-blocking of Q0 end. Now, if I am, please remember, if I am using always block with a event like passage of clock or negate of clock, definitely the compiler or the tool is going to yield a flip-flop logic. The compiler is going to yield a flip-flop logic. And here, if we are simply writing Q0 is equal to S underscore n, a D flip-flop is yielded. In the both cases, a D flip-flop will be given by our synthesizer because we are writing always at the rate passage of clock. A clocking edge, a flip flop, a simple flip flop will be given. Okay, a D flip flop will be synthesized by our tool. Now, if we are using a blocking assignment, then what is going to happen? At the first stage, your output Q0 will be given to input. So input will be given to Q0. So at the first, this particular updation is going to happen. Then after only your Q1 will be updated to Q0. So if you want to see the diagram, how it is going to look like, it is going to look like this. So this is a single D flip flop where your input is S underscore in, and this is your Q0, and this will be your Q1. So Q0 and Q1 will be connected to a single line. Why single line? Because after Q0 value updated, after the value of Q0 has been updated, then only compiler is going to second line and it is going to have this assignment, and it is assigning Q0 to Q1. So you can see at the first passage of clock only the value of Q0 will be equal to 0 and the value of Q0 will be Q1 will be equal to 1. So in this example, in the previous example, if we want to see this clock Q0 and Q1, initially they will be equal to 0, and at the first clock edge we will get the Q0 value as 1 and Q1 value also will get 1 only. But this is not the behavior we want. We want 1 0. But if we are using a blocking assignment, this is what we are going to get. But if we are using a non-blocking assignment, then what is going to happen? These two values or these two assignments are going to happen parallelly. Then what happens? The Q0 value will be updated to the present value of S underscore in. That is Q0 will be assigned to 1 and Q1 value will be updated to the previous value of Q0 since we are using a non-blocking assignment, right? So Q1 will be still 0 only. And if you want to see the diagram of this second case, this is how it is going to look like. Two D flip-flops will be yielded with two passage of with the positive edge of the clock connected to both the flip-flops, and here we are going to give in, and here we are going to get Q0, and here we are going to get Q1. So this is the difference between your blocking assignments and non-blocking assignments. So this is how your design is going to look like if you are going to use a blocking assignment and if you are going to use a non-blocking assignment. So that is why it is preferred to use non-blocking assignments in sequential logic, whereas it is preferred to use blocking assignments in combinational logic. That is the reason we have this particular set of rule that blocking assignments should be used in combinational design, whereas non-blocking assignments should be used in the sequential design. Now let us start writing our counter code. First, let us try to write down mod 4 counter, mod 8 counter, and mod 16 counter. Next, we will write down the codes for mod 3 counter, mod 5 counter, and let's write the code for mod 9 counter. Okay. Next, after this, what we are going to do is we are going to, okay. First of all, this all counters which we are going to develop, these are all synchronous counters which we will discuss. Okay. Synchronous counters, and that is we will discuss up counter, synchronous up counter, synchronous down counter, and up down counter. Okay, so let us try to write all the codes for this. Then after we will discuss frequency divisions. Frequency division by 2, by 4, by 8, and by 3, and by 5, and by 9. After this we will discuss by 1.5, by 2.5. Okay. Yes, so this is the plan which we are going to discuss. Now let us try to write down the code of our mod 4 counter. So for writing down the code for mod 4 counter, how to write the code for your mod 4 counter? Mod 4 counter. So this mod 4 counter is going to look like this, the block diagram, where you are going to have clock, reset, and output as count, which is of 2 bits. So mod 4 counter is going to count from 0 0, 0 1, 1 0 and 1 1. Let's take one enable signal. If this enable is equal to 1, then only we are going to count, or else we will not make this count to increment. Okay. Let us write down the code for this. So module counter underscore mod 4 input clock reset, and we are going to have enable signal and output 1 down to 0 count. Okay. Now first of all, let us declare a internal variable, or okay, no issue, we will declare them as reg. Okay. Always at the rate passage of clock begin. If I apply my reset signal, then begin, my count will be equal to 0. See, I am using a non-blocking assignment. Else if enable is equal to 1, my count will be incremented. Count is equal to count plus 1. Else count should not increment. Count is equal to count itself, and followed by end, and followed by end module. So this is my code which I have written. So let me create, let me open this Vivado tool and let me execute here in the tool. So this is a simple count logic I have written. If reset my count is equal to 0, else my count will be incremented and count will be equal to count. So what is going to happen initially, your count value will be equal to 0, then it will be increment to 1, next to 2, next we will reach 3. 3 is nothing but 1 1. Then if we are going to add one more 1, then it is nothing but 0 we are going to get. So since it is a 2-bit, we are only going to see this 2 zeros. Okay, we are not going to see this one. Okay, so that's why after 1 1 we are going to get 0 0. So no need to write any condition, just write down count is equal to count plus 1. Okay, yes. So let us check this. So before that, we will write down the test bench for this one also. So how to write the test bench module counter underscore mod 4 underscore tb rich clock comma reset comma enable and wire count, and wire it should be of 2-bit 1 down to 0. Okay, now I will instantiate my design counter underscore mod 4 dut clock comma reset comma enable comma count. Okay, and let me first of all initialize my variables. Initial begin clock reset and enable is equal to 0, and within another initial beginning block, first of all I should generate my clock. How to generate my clock? Always #5 clock is equal to not of clock. Okay, next I'm going to reset my design. Reset is equal to 1, then after some time unit I will apply my reset is equal to 0. Next I will apply my enable signal is equal to 1. Let's say after 10 time units I'm going to apply my enable signal equal to 0. That is, I'm going to end my count, and followed by end module. So let me copy this code and let us create a file in the Vivado. Counter underscore mod 4 is my module name, and followed by finish. Press OK and press yes. Let us check our output, how it is going to look like. So initially my count is equal to 0, count is equal to 1, then my enable was made to 0. So that's why my count is not getting incremented. So let us say, let us take this enable signal, let's keep it for long time. Let's say for 50 cycles. Let me save this and run this again. And let us check it out. So your count is equal to initially 0, next 1, next 2, next 3, next 0, 1. So again my enable was made to 0, so that's why my count is not getting incremented. So this is how we are going to increment our mod 4 counter. Now in our next session we are going to discuss how to implement your mod 8, mod 16, mod 3, mod 5, mod 9. We will discuss them one by one. So we have discussed our synchronous up counter. Next, we will discuss this counters in our next session. Okay. Yes. So that's all about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel. All about VLSI. Thank you for watching this video.